Today, we're becoming chemical detectives. Our mission? To take a totally unknown substance and, with just a few clever tests, figure out exactly what it is. This isn't just about chemistry, It's about following the clues and cracking a code. So, let's get this investigation started.
So, picture this. Someone hands you this vial. It's just a plain white powder. And the only question is, what on earth is this? This is our case, and just like any good detective, we can't just guess. We need a system, a plan of attack to crack it wide open.
Now, the official name for this whole process is qualitative salt analysis. But honestly, let's just call it what it is: chemical forensics. Our job is to ID the two suspects that make up our mystery salt: the anion, which is the acid radical, and the cation, its basic partner. This whole system of tests, well, that's our forensic toolkit. All right, so here's our game plan. First, we're going to learn the master detective's mantra for cracking any case. Then we'll go on the hunt for our first suspect, the anion. After that, we'll track down its accomplice, the cation. And we'll wrap it all up by filing our final detective's report, packed with some crucial tips for your own investigations. Every great detective has a core method, a mantra they stick to no matter what. So let's take a look at ours.
This right here, this is the secret sauce. It's a 3-step loop you'll do over and over again. First, you run a test. Second, you make an observation, and I mean you write down exactly what you see, no guesswork. Then, and only then, you make an inference. That's your logical deduction about what that observation means. Test, observation, inference. That's the heartbeat of our investigation.
Okay, time to get our hands dirty. Let's start the hunt. Our first target is the anion, the so-called acid radical. We've got to find this first piece of the puzzle. In any investigation, you always start with the usual suspects, right? Well, in the world of anions, carbonate is definitely a usual suspect. So let's see if we can find its chemical fingerprint.
The procedure itself is super simple. We just take a tiny bit of our mystery salt, drop it in a test tube, and add a little dilute hydrochloric acid. And now, we watch. We watch very, very closely to see what happens.
And this is where our 3-step mantra really shines. Our observation? Brisk effervescence, which is just a fancy way of saying it's fizzing like crazy. That fizz tells us a gas is being made. So our inference is that carbonate might be here, but to be sure, we need to confirm it. We bubble that gas through something called lime water. And if that lime water turns milky, that, my friends, is the smoking gun. Case closed. Carbonate is confirmed. Okay, but what if it's not carbonate? Let's bring in a couple of other common culprits, the halides, like chloride and bromide. For these guys, we need to use a stronger acid, concentrated sulfuric acid. And what's so cool here is that the observation immediately gives us a lead. If you see a colorless gas, you should be thinking chloride. But if you see reddish-brown fumes, that's a huge clue pointing towards bromide. See? We're already narrowing it down. Now, those fumes are a great lead, for sure, but they're not enough to close the case. We need a definitive confirmatory test. So it's time to bring in our special interrogator, silver nitrate. And this is what makes it a confirmatory test. When we add that silver nitrate, a chloride ion just can't hide. It forms this thick, curdy white solid called a precipitate. A bromide ion, on the other hand, forms a pale yellow one. The color is everything. It's the key piece of evidence that tells us exactly which halide we're dealing with. Absolutely no doubt about it. Let's bring in one more high-profile suspect, the nitrate ion. Its confirmatory test is probably one of the most famous in all of chemistry, mainly because the result is just so unique. It's like a chemical signature. And this is the famous brown ring test. We add some fresh iron sulfate solution, and then, very carefully, we let some concentrated sulfuric acid trickle down the side of the test tube. If nitrate is present, you get this beautiful, unmistakable brown ring right where the two liquids meet. When you see that ring, bam, you know for sure you found nitrate.
So we've ID'd our anion. Great. But every anion has a partner in crime, a cation. So now we start phase 2 of the investigation, tracking down this accomplice by working our way through different groups of suspects.
And here is our lineup of suspects. Now, to make the search easier, chemists have organized cations into these groups based on how they react to certain chemicals. Our job is to go through them group by group and see where our mystery cation is hiding.
So let me show you how this works. We're going to start by checking if our suspect belongs to group 2.
This test will either tell us to keep digging into this group, or it'll tell us that they all have a solid alibi.
So we take our solution, add some dilute HCl, and then bubble in some hydrogen sulfide gas. We wait, and our observation is nothing. Nothing happens. No solid forms. Now listen, in an investigation, a negative result is just as important as a positive one. Our inference here is crystal clear. Group 2 is absent. They all have an alibi. We can cross them right off our list.
And just like that, our list of suspects gets shorter. See, by proving that Group 2 is not there, we've actually made some serious progress. We can now move on to the next group in the lineup and not waste any more time on these innocent ions. So what does it look like when we do finally get a hit? A positive ID? Well, let's say we've moved on, and now we're testing for Group 3, which has suspects like aluminum and iron in it.
For this test, we add ammonium chloride and ammonium hydroxide. And this time, we get a reaction. Our observation is a gelatinous white precipitate. Basically, a distinct, kind of jelly-like solid appears. This is the clue we've been waiting for. Our inference? Group 3 is present. And that specific gooey white appearance points right at the aluminum ion. We've found our accomplice. We've identified the anion and we've identified the cation. Case closed. Now it's time to file our final report and focus on the key takeaways that are going to help you succeed when you're the one in the hot seat during an exam. Okay, if you remember just one thing from all of this, let it be this. When you write up your results for an exam, always use this format. State the test you did, clearly describe your observation, and then write your logical inference. That structure proves you know what you're doing, and it's exactly what the people grading your paper are looking for. And if you're looking for where to focus your study time, make sure you have these two cases absolutely nailed down. The lime water test for carbonate and that classic brown ring test for nitrate. They're classics for a reason, they're reliable, they're visually obvious, and they show up on exams all the time. Master these two and you're already ahead of the game.
So there you have it. We've seen how this systematic, logical approach of test, observation, and inference can solve a pretty tough chemical mystery. It's a really powerful way of thinking that goes way beyond the chemistry lab. So the real question is, now that you have the tools of a detective, what other mysteries could you solve?